Introduced the EE Colloquium speaker, Ito Walks, from the University of Maryland. Ito received his undergraduate degree and master's at Johns Hopkins and went on to get his PhD at Stanford before going on to University of Maryland, where he's now a professor in the ECE department and also a member of the Joint Quantum Institute. He, in his early career, was the recipient of numerous awards, including the Presidential Early Career Award for Scientists and Engineers, and also the Young Investigator Award from the Army Research?
Yes.
Yes, from the Army Research Office. And also, very recently, he was elected as a fellow to the American Physical Society. He is one of the world leaders in extreme nonlinear optics. And what I mean in this case is nonlinear optics at extremely low light levels, even down to the single photon level. So join me in welcoming Ito as today's speaker. Thanks.
Thank you. Okay, so you can hear me with the microphone, right? I want to thank Kaimi, Arka, and Xiaodong for inviting me here. Thanks also for the introduction. It's always interesting to hear somebody say, in his early career, and then you won an award some time ago, and then I have to think back about when and what that was. So I guess it's a sign that the years are going by fast. But it's really lovely to be here. Actually, it's amazing. You guys have great. Every time I visit Seattle, it's beautiful weather, and you keep telling people tell me it's always raining here, but I've just never seen it. I've never seen a raindrop in Seattle, so I'm just wondering if this is some giant conspiracy for you to keep people away, or I don't know what what it is. But regardless, it's a real pleasure to be here and tell you a little bit about what we do at the University of Maryland. I'm a professor in the electrical engineering department. I'm also a fellow of the Joint Quantum Institute at the University of Maryland. That is a large institute that hosts a collaboration of many researchers, both from the University of Maryland Physics and Engineering Department and also from NIST Gaithersburg. The tying theme is that we're all really working on different facets of quantum physics and, in some cases, quantum information. So let me begin with a kind of motivation for what we are trying to do. It's well known within my community and probably among many of you that for quantum information processing, it's really important to have strong interactions between atoms and photons. One of the reasons for this is because atoms are good sources of photons, and they're also good quantum memories. So they're right now the best platform for storing quantum information over long times, while photons are good information carriers. They can transmit over optical fibers very long distances to mediate interactions between the different memories, and that's really the general idea behind quantum networks, where one could imagine in the future having banks of quantum memories interacting by photons, possibly traveling over optical fibers. I want to mention, though, that this picture has an interesting duality. Just as photons are very good at mediating interactions between atoms, atoms are very good at mediating interactions between photons. Photons, in general, don't interact. They have no mass or charge. So if you do want to do something interesting with them, some form of computation, either classical or quantum, you need to be able to get them to somehow nonlinearly interact with each other. And here, the atom is the intermediate. You use it as a mediator between the interactions, to mediate the interaction between photons. And that's at the heart of many ideas in photonic quantum computation. So the point is, both of these pictures, both of these ideas, at their heart require some way to get strong interactions between atoms and photons. Now, in our group, we don't work with real atoms. There are people at the Joint Quantum Institute that are very good at working with real atoms. They work with magneto-optic traps or chains of trapped ions. But in our group, we try to come up with solid-state equivalents of atoms, because we hope that these kinds of equivalent atom-like systems can eventually integrate into some sort of semiconductor chip and make a real device. And I'm in the engineering department, so devices are kind of one of the things we really want to go after. So we use various emitters in my group, but one of the main workhorses of our research is the semiconductor quantum dot. This is a picture of a atomic force microscope image of a surface containing quantum dots. These are indium arsenide quantum dots. Each one of them is about 30 nanometers in diameter, 5 nanometers in height, and they act as local traps for electrons and holes. And the confinement is sufficiently tight that they exhibit discrete energy level structures that can be excited and controlled by light the same way as real atoms. And that gives us a very nice system to work with on a semiconductor chip. One of the really good features of quantum dots is that they exhibit very efficient and pristine photon emission. As a matter of fact, they hold the world record for simultaneous efficiency and indistinguishability of single photons. By indistinguishability, I mean photons that emit at the same frequency and the same wave function. As a matter of fact, I gave a talk in Paris about a year ago, and these are numbers already, that's one of the groups that does some of the best work in this, and these numbers are actually already quite outdated. They're exceeding 95%, so I got a little bit of flack for not having updated my numbers, but it's rapidly progressing. At the same time, just as quantum dots are good emitters, they also can act as qubits. And here, the key is to add some sort of quantum degree of freedom. And in solid state, the best one is usually spin, because spin usually has the best coherence properties. You can add a spin to a quantum dot by adding an additional carrier to it, so charging it, making it positively or negatively charged. In this case, the illustration shows a negatively charged quantum dot where an extra electron is injected into the conduction band. And this can be done various ways, by electrostatic gating or by doping or by optical injection. There are a lot of different techniques, and there's a vast body of work going for the past 15 years on how to charge and manipulate a quantum dot spin. Once you put that charge into the quantum dot, you then have two stable ground states corresponding to the spin of the added carrier, and those two ground states can serve as qubit states. They can store quantum information. At the same time, they can radiatively be excited to these excited states called tryons. So the spin can actually talk to photons through these optical transitions, and that provides a very interesting system for us to get photons to talk to spins. And one of the goals of our group is to push that to the single photon, single spin level. So we want one photon to talk to one spin. And that requires an extreme degree of light-matter interaction that conceivably you can only achieve using an optical cavity. The idea is that the optical cavity stores photons and increases the interaction time with the quantum dots so that you can get a strong interaction, and also confines the electromagnetic mode to a small volume, so you get a very high field intensity. And whenever you put any kind of atomic system in an optical cavity, if you want to know how strong the interaction you're going to get is, there are really three important figures of merit or parameters that characterize your interactions. The first is the cavity quantum dot coupling strength. This is the rate of coherent interaction between the cavity mode, the cavity photon, and the quantum dot. So you may envision this as the rate of coherent evolution in the Hamiltonian that coherently and reversibly exchanges energy between the emitter, the atom, or the dot, and the photon. But on top of that, there are two important decoherence mechanisms that destroy the coherence of the state. One is the dipole decay rate. So the dipole can either radiatively or non-radiatively decay, or it can radiatively decay into undesirable modes that are not the cavity mode. And it can also dephase due to interactions with phonons and other parasitic effects. And the second is the cavity field decay rate. So the photon in the cavity can leak out. And if it leaks out, it's a loss of coherence. The figure of merit that tells you whether you're getting weak or strong interactions is a number called the atomic cooperativity. And as you'll see, it's basically a ratio of the coherent coupling strength squared divided by the product of the two decoherence rates. And in the case where the cooperativity is very small, the interactions are weak. So if you looked at the transmission spectrum of a cavity, what you'd see is basically something very similar to an empty cavity. You would see just a simple Lorentzian transmission. On resonance, on resonance you would have 100% transmission because it's a resonant cavity. And the line width of the transmission is simply given by the cavity decay rate. So this is simply a Fabry-Perot spectrum, nothing really surprising or interesting. But if you get into the high cooperativity regime, where this number is much bigger than 1, something interesting happens. The cavity reverts from being this simple Lorentzian spectrum to what appears to be a doublet. And on resonance, photons actually cannot transmit through the cavity. They all get reflected. So the quantum dot, or the atom, it prevents photons from entering the cavity. So in the high cooperativity regime, a single atom can prevent a photon from going into the cavity. For a large number of atoms, this is not a surprising effect. Think about a Fabry-Perot cavity where you send in light and then stick your hand into the cavity. What you've done is you've basically shut off the resonance, and now it just looks like a mirror, so everything reflects. But cooperativity will tell you, a high cooperativity regime tells you that you don't need to stick your entire hand into the cavity. Putting one atom into the cavity is enough to change that transmission from being perfectly transmitting to perfectly reflecting. Okay, so why is this effect so interesting? Well, it allows us to build an interface between spins and photons, what we call a quantum transistor. And the idea here is that instead of just putting a simple dot that behaves as a two-level cavity, we put a dot with a charged dot in it, a dot that carries the spin degree of freedom. And now we have a more complicated level structure inside of the cavity. We have an emitter that has two stable ground states, spin up and spin down. But let's presume for the moment, I'll explain to you how it's done later, but let's presume for the moment only one of these transitions can couple to the cavity because of either selection rules or detuning. So only when the emitter is in the spin-up state can it couple to the cavity, whereas in the spin-down state, it's decoupled. It's basically, the cavity appears empty. So in this case, if you put the emitter, the quantum dot, in its spin-down state, the spectrum, again, appears to be that of an empty cavity because there's no absorption. The dot can't absorb light. And so a photon that is on resonance will transmit. That's just simply the property of an empty resonant cavity, of a bare resonant cavity. But if I flip the spin from spin up to spin down, I've created a completely different situation. Now, you can absorb a significant amount of light in the cavity, and if the cooperativity is high, again, you'll get this modified spectrum. Instead of the photon transmitting, it now reflects. So this behaves as a single spin switch for photons. The spin of the dot determines whether photons will transmit or reflect through the cavity. And so that's why we call it a transistor. It's very analogous. It's kind of analogous to the kind of transistors we use in computers, in that, but instead of a gate voltage, we're using a single spin to do the switching. And that's very important because unlike the gate voltages in your standard CMOS transistors, the spin is a quantum object, and it can exhibit quantum mechanical superposition. And because of that, it's actually, this kind of transistor actually allows you to create strong interactions between photons. And to give you an example of how that works, here's a way to use the transistor to entangle two photons that are previously unentangled. So that usually would require some very, very strong Kerr nonlinearity between the two photons. But I'll show you that this transistor gives you that kind of so-called Kerr nonlinearity. The idea is that instead of preparing the spin either in its spin up or its spin down state, we now use the fact that it's a quantum variable to put it in a quantum superposition of spin up and spin down. And so now when the photon reflects, it both transmits and reflects at the same time. In fact, it becomes entangled with the internal degree of freedom of the spin. If the spin is spin up, it reflects. If the spin is spin down, it transmits, and you get this quantum entangled state. Then we send a second photon in. It will also both reflect and transmit. However, it will always go in the same direction as the first photon, because if the first photon reflected, the spin is spin up. The second photon must also reflect. as long as there was no undesirable spin flip event during this time. Similarly, if it transmitted, spin must have been in spin down. And so after measuring the spin, you end up with an entangled state of the two photons. So by using this cavity-mediated interaction, you took two independent photons and entangled them. And that in itself is a complete universal quantum operation. And in fact, you can continue to do this with more photons. You don't have to stop at two. You can repeat the process over and over and over again, and you can start to generate these large multi-photon entangled states, provided that you can maintain the degree of coherence and you have the fidelities of all these operations that are needed. And in fact, if you are a little more clever, and you control both the evolution of the dot and the reflection of the photons together, you can actually build cluster states. And there's been some this is based on an original idea by Lindner and Rudolph from 2009 that was recently realized in a science paper from David Gershoni's group using a slightly different system based on a dark exciton. But the idea is analogous here. By using this kind of shotgun approach, you can actually stitch together complex cluster states, and once you do that, you can do universal quantum computation. Of course, this is all very difficult because in order to do that, you have to make sure that the fidelity of your spin is very high and that the efficiency is high enough. So there's a lot of challenges to realizing this kind of a scalable nonlinearity. And when we started this, we weren't there yet. We just wanted to demonstrate the fundamental transistor action and then work from there. So the first thing we needed was some sort of optical cavity that gives us this high cooperativity. And for high cooperativity, you need cavities with small mode volumes and high quality factors. There are various ways to do it. We use a photonic crystal cavity structure. These are cavities made by patterning a periodic array of air holes into the matrix, into a gallium arsenide substrate. So we use E-beam lithography to pattern this periodic array of holes, and we create a defect intentionally in the center of this periodic array. This is a top view. This is a cross-sectional view. You can see what we're doing is actually drilling holes into a thin membrane of gallium arsenide. And the idea here is that in the in-plane direction, the photonic crystal always reflects photons back into this defect region because of Bragg reflection. In the out-of-plane direction, the photon is confined by total internal reflection, so it bounces off the surface at some angle below the total internal reflection angle. By combining Bragg reflection in the in-plane direction and total internal reflection in the out-of-plane direction, we get three-dimensional electromagnetic confinement. And then all we need to do is put a dot at the center of this cavity where the field is highest, and we can get very strong interactions between atoms and between the dot and the cavity mode. And that's not an easy thing to do because the dots are randomly distributed on the surface, and also the dots have inhomogeneous broadening, which means they all have slightly different wavelengths. Later in the talk, I'll show you how we can potentially get around many of these problems. We've actually made progress on that. But when we're just trying to make a single device, we actually do something very sloppy. We simply make many, many cavities, and we try to find one that has a dot strongly coupled to this cavity mode so that we see these high cooperativity effects. And fortunately, we can identify that device simply from the spectroscopy. Sorry. Okay, this slide is not important. That one is should have been taken out. So how do we identify when there's a dot? We have to have a dot in the cavity. It has to have the right wavelength, and it has to be charged. And in our case, just a fraction of the dots are charged due to residual doping. And the way we identify that is by looking at the spectrum. So this is the spectrum of a cavity and a nearby quantum dot. And what we do is we turn on a magnetic field. So this is what happens when you apply a 3 Tesla magnetic field. And then this is a 5 Tesla magnetic field. And what you see is that this single line breaks up into four lines. And when we see that, we immediately know that the dot is charged, because these 4 lines correspond to these 4 optical transitions. So as soon as we see that, we know that we have a dot that is charged and there's a spin degree of freedom. We can further verify it, as I'll show you in the subsequent data, but this is already, it makes it clear to us that we have a single charged dot. Then we can tune the dot onto the cavity by applying a proper magnetic field. So in this case, 6.6 Tesla tunes transition sigma 1 onto cavity resonance, while all the other transitions are detuned. And this is how we get this condition that I was mentioning earlier, that only one of the spins can couple to the cavity while the others cannot. Only transition sigma 1, that I label here sigma 1, is resonant. All the other ones are detuned, so they don't resonantly couple to the cavity. And then we can just look at the reflection spectrum and see if we get a spin-dependent reflectivity and whether we have these high cooperativity effects. And so the way we do that is by looking at the reflection spectrum. I should point out that there's a subtlety here. In our experiments, we actually have a DBR under our cavity, which causes all of the light to reflect up. So our cavity actually behaves like a single-sided cavity, not like a double-sided cavity, where things can transmit and reflect. But it turns out by using polarization interferometry, we can effectively achieve a device that behaves as a double-sided cavity, where horizontal and vertical polarization represent the two input ports of the cavity. So if light is, we can inject the cavity with horizontal or vertical photons, and because of properties of the cavity, specifically that it has a optical mode that is polarized along the axis of the cavity, we can actually determine whether the light coupled or not by whether it comes out with a horizontal or vertical polarization. The details of that are not too important for this talk. What is important is that basically, rather than looking at whether light transmits through the cavity or reflects from the cavity, we look at whether light transmits or reflects from a subsequent polarizer. And the situation is completely analogous to a double-sided cavity. It's mathematically an identical system. It's just easier for us to do because we can do all of our measurements by looking from the top of the sample rather than having to measure what goes through the sample. That's not an easy way for us to access our device. OK, so the first thing we can do is we can simply optically pump the spin into one of its spin states, say spin down. And in this case, the cavity should basically look empty. It should look like a Lorentzian line shape. And that's exactly what we see. We see this kind of Lorentzian line shape, which is consistent with a bare cavity, where the line width gives us, it's determined by the Q of the cavity. We can then, and then on resonance, this basically is telling us that most of the light is transmitted through the polarizer. But we can pump the other spin state. We can prepare it in the spin down state. And in this case, we see a spectrum that looks like something where you have an atom coupled with high cooperativity to the cavity mode. We see this suppression, this reflection. And this is actually reflection, not absorption. We can do it we can monitor it by looking at the light reflected from the other polarizer, and we'll see that the light here is not lost to absorption. It's actually lost to reflection of the polarizer. And so again, now we have a suppression of the transmission through the polarizer. And so we have a spin-dependent reflectivity, a spin-dependent reflection spectrum. The polarization of the photon rotates depending on the state of the spin. Now that's kind of, that's an incoherent way to prepare the spin. We either pump it into spin up or spin down. We'd like to be able to prepare the spin anywhere along the Bloch sphere. And there's a standard way to do this. It's a technique known as Ramsey interferometry. It utilizes, so basically the way it works is we first optically pump the spin into the spin up state, and then we utilize two optical rotation pulses. The way we actually tip the spins in this case is we used fast picosecond pulses, which create via a Raman transition in order to create an effective Rabi oscillation between the two spin states. And so the first rotation pulse will rotate the spin onto the equator of the Bloch sphere. And now we have a magnetic field applied of about 6.6 Tesla. So what the spin is going to do is it's going to start to precess along the equator of the Bloch sphere due to the magnetic field. If we wait for an integer number of precessions, then the second rotation pulse will rotate it to its spin up state. And then we can see that by probing the reflectivity with a subsequent photon. However, we can wait a different amount of time between the two pulses. We can wait an integer plus 1/2 oscillations along the Bloch sphere. Then we end up on this side, and afterwards, the rotation pulse will rotate it to the spin down state. And of course, if we wait some time in between, we'll get some intermediate condition. So if we simply plot the reflectivity of the cavity is a function of the delay between these two pulses, we'll see this oscillation. This oscillation is electron spin resonance, but it's measured in a very interesting way. It's measured by looking at how much light reflects from the cavity, not by directly probing the electron spin through some sort of inductor. So it's an optical way to probe the spin on very fast timescales, because you can see that this is oscillating at the Larmor precession period is something like 30 picoseconds. Okay, that still doesn't, so that tells us that the spin is, there's a coherent spin inside, then it controls the photons. It doesn't yet tell us that this is a quantum switch. Because if this was a quantum switch, we would have one other ingredient. We would have a back action of the photon on the spin. If this, whenever you have a quantum system where two objects interact, there's always a back action. If we measure the spin, the photon should impose some sort of measurement back action on it. And that's actually true. Because this is a quantum switch, just as the spin can control whether a photon transmits or reflects, the photon can also flip the spin. And the way it works is as follows. We use the same Ramsey pulse sequence as before. So two pulses separated by a delay. And we probe the spin state. And this black curve is just showing you the Ramsey oscillations that I showed before, just taken on a much closer, on a much shorter time scale. So you're seeing a close-up of one period of the Ramsey oscillation. And then, if we reflect a photon in between these two pulses, because this is a quantum interaction, the photon actually imposes a pi phase shift on the spin. That corresponds to an additional half rotation across the Bloch sphere, which manifests itself in a 90-degree shift of the Ramsey oscillations. So the additional photon will flip the spin from being in the spin-up state to being in the spin-down state. Now, of course, you see it's not perfect because we have finite fidelity of the spin in the switch and also finite fidelity of the finite cooperativity. So we don't get a perfect 0-to-1 drop, but you can clearly see that there's a strong measurement back action where the final state of the spin, originally supposed to be in the spin-up state, now is in the spin-down state. So just like a spin can control the photon can control the spin. And that, if you combine those two, then you can get what we call a deterministic photon-photon switch. You can get one photon to control another photon with an ideal device deterministically. And the idea is the first photon sets the spin state, either to spin up or spin down. And then that spin state acts, and that photon we refer to as the gate photon. That spin state, after this pulse sequence, then acts on the signal photon. So if the first photon set the spin and spin up, so if there was no photon, if there's no gate photon, the spin is in spin up. That causes one reflection amplitude. If there's one photon in the gate pulse, it goes to spin down. That causes another reflection amplitude. And so by basically combining these two steps, one after the other, we can get a photon-photon switch, where one photon determines whether a second one will transmit or reflect through the cavity. And you can see, again, the contrast is about 30–40%, so it's not perfect, and that's because, again, we don't have perfect single spin rotations, and our cooperativity is not infinite, but this is still a very strong nonlinearity. This is one photon basically increasing the probability that another photon reflects through the cavity by 50%. And so this is one way. If with straightforward improvement, we could get this. One can get this to have a very high contrast. So this is one way to get really deterministic photon-photon interactions. But there's kind of one other interesting aspect about this photon-photon switch, and that is that we have an internal quantum memory in the system, and because of that, we don't have to, it enables it to act as what we call a single photon transistor. So let me explain to you what is the difference between a switch and a transistor. In a switch, you have a strong control signal, control that controls a weak signal. That's usually what we refer to in engineering as a switch. Transistor is the opposite. You have a weak control signal, control that switches a large signal. And that's what you need typically to get scalable circuits. That's what gives you gain That's what gives you fan out. And so for a single photon transistor, that means that one photon not only switches a second photon, but it means one photon can switch many photons. If you can do that, then you have not just a switch, but a transistor. And fundamentally, you cannot achieve that without some sort of internal memory element. There's a fundamental time bandwidth trade-off that if you just put a two-level system in a cavity, you can never get a transistor. As a matter of fact, you cannot even get a deterministic switch. But we do have a memory. We have the spin, and it can mediate these interactions. So what we did was we simply cranked up the amplitude of the signal to see if we could continue to switch when we have more than one photon on average. And so here's the same data shown for an average of 2.1, 5.3, and 11.2 photons. And you can see that there is still a switching contrast, although it's degraded. And the reason why this degradation happens is because each signal photon that reflects off the cavity can cause an undesirable Raman scattering event that flips the spin. So the switching signal itself can actually flip the spin through Raman scattering. And each photon has a small probability of doing that. And that probability dictates how strong of a signal you can actually switch. If you go beyond that, then the signal itself is already affecting the switch, which is not what you want. So we simply look at the switching contrast as a function of photon number, and it exhibits this kind of exponential decay, and it has an exponential decay constant of about 13.8 photons. So from that, you can estimate that the average number of photons you can scatter off of the cavity before the signal itself creates an undesired self-switching event is on the order of 14. So that is the limit of this transistor. You can switch, on average, 14 photons given one photon. And beyond that, the signal is just too strong, and the switch itself can't handle it. OK, so that kind of gives you an idea of how, by putting a single spin in a cavity, we can start to get these very strong photon and photon interactions. Now, everything I've talked to you so far has been about single devices operating at near-infrared wavelengths of about 920 nanometers. For the rest of the talk, I'll describe to you some of the work we've been doing towards scaling this into bigger systems composed of more switches that maybe interact with each other using photonic circuits or communicate over optical fibers. And so the first problem we have is that all of our indium arsenide, gallium arsenide quantum dots, they operate at the wrong wavelength for fiber. And a lot of what we're interested in is coupling them to fibers and using fiber networks. As a matter of fact, we have a large project between the Joint Quantum Institute and the Army Research Lab to create a kind of a basic element of a quantum network over 5-10 kilometers of dark fiber that connects the two labs. But for that, we can't work at 920. The fiber losses are too large. We have to push things to telecom wavelength. So as a collaboration with the Laboratory for Physical Sciences at the University of Maryland, who has MBE growth facilities, we've been working on developing new material, a different class of materials, indium arsenide, indium phosphide dots, which emit at longer wavelengths. So these dots emit at 1.3 to 1.5 microns, and they have these sharp lines correspond to a single dot emission. So these dots were grown at the Laboratories for Physical Sciences by Chris Richardson and Richard Levitt, and we've been working on trying to use them to kind of implement some of the many devices that I showed you previously, but this material is not as well developed as the gallium arsenide system. So before we decided to try to look for spin and transistors and all of that, we figured we'd just see whether we can couple them to cavities and make good sources of single photons. And so the first thing we did was we coupled them to a photonic crystal cavity and tried to use it to simply enhance the single photon emission and get a bright source of single photons. Here, we employed a little bit of a trick. We used a higher order mode of the photonic crystal cavity so that it emits photons whose transverse mode is very Gaussian-like, which is good for coupling it to fiber. One of the problems we have with cavity structures we've been using at shorter wavelengths is that they kind of emit at an angle. And so if you try to focus them onto a fiber, you really run into problems. But if you use different modes of the cavity, that can be significantly mitigated. And so using this cavity structure, we could see very good single photon emission, and we could see 2 order of magnitude enhancement in brightness. So if you look at a dot in the bulk, which is the red line here, versus a dot in the cavity, we see a 2 order of magnitude enhancement in brightness, and we get count rates of about 1.5 million counts per second on our detectors. This was at the time, and I think still might be, the brightest single photon source at that particular wavelength. And this was done using very poor detectors. These were in-gas avalanche photodiodes that operate at 1.3, 1.5 microns. They have an efficiency of only about 10%. We now have superconducting nanowire detectors that have 80% efficiency at this wavelength. That should improve this count rate by a factor of 7 to 8, and we're actually seeing that. So this is an older result. We expect that we can really get this count rate up in the tens of millions. And so we have single devices. Now the question is, can you get multiple devices and connect them together? And the answer is, you can go into the clean room and draw as many devices as you want. You can draw thousands of devices. But you're always going to run into a big problem. And that is that the dots are distributed randomly on the surface, so many of these devices won't even have a dot in them. And you also have a lot of spectral randomness. So even the few that have dots in them, dots are not necessarily in the right place. And so the yield that we have is about 5%. 5% of our devices have a dot at the right place with the right wavelength. So if you try to make a device made of 2 cavities, your success rate is 5% squared. If you tried 3 cavities, it's 5% cubed. And as a matter of fact, even with 2 cavities, my graduate students give up, and they tell me that they're not doing it. And they tell me what to go do with myself. So we have to be a little more careful, a little more clever about how we do this. And the first thing so as far as the spatial randomness, there are actually a lot of good solutions for that now. People have come up with very efficient ways to do site-localized dots without degrading the line width of the dots significantly. There's some very good recent work at NRL where they've succeeded in getting below 30 micro EV site-localized dot growth. But even if you can site-localize it, you still have to deal with the spectral randomness. Even if you get the dot in the right place, it still won't be the right frequency. For that, you really have to incorporate some sort of on-chip tuning. And we decided to start with the simplest and oldest way, which is using on-chip thermal tuners. And we're not even doing anything as fancy as running current through the device in order to create on-chip thermal tuning. We're actually just creating metal pads, and we shine lasers on them, and the laser just heats that area, and that causes a shift of the band gap, which tunes the dots. It's not the best way to tune the dots because as you heat them, you increase the phonon scattering rate and you broaden the line width, but over a reasonable range, you can actually get some tunability. And in fact, this is a device where we have 2 cavities separated by about 5-10 microns, and each one of them contains a dot. So 2 cavities, each cavity has a dot in it, and we're able to tune the 2 dots onto each other by thermally tuning one of the cavities. And we use these thermal isolation tethers to make sure that when we heat this cavity, we don't inadvertently heat this cavity. And so we can get their line widths to match almost perfectly. And then when we do a second order correlation measurement, a G2 measurement, in order to determine whether they emit indistinguishable photons of the same color and the same wavelength, we see this two photon interference effect. We see this bunching, which tells us that they're emitting indistinguishable photons. Now, in an ideal case, we wouldn't see a sharp peak. We would just see a flat line when they're indistinguishable, and a dip to 50% when they're distinguishable. In this case, we have this very narrow, sharp peak. That's almost always an indication that there's dephasing in your system. And in our case, we know why it's there. It's because we're exciting the dots with a very high energy laser, and we're creating carriers we're creating free carriers near the dot, which then randomly diffuse into the dot, land in the ground state, and emit. And there's a time jitter associated with that. The amount of time it takes one dot to capture an electron hole pair and emit is different than the amount of time it takes another dot, so they don't emit exactly at the same time. And that creates tremendous jitter, which causes a lot of dephasing. The way to get around that is to do resonant or quasi-resonant excitation. We didn't do that with this dot because we didn't have the lasers. We have lots of lasers at 700 to 1,000. We didn't have a resonant or quasi-resonant pulsed 1.3 micron laser that we could do this experiment with. We now have those lasers, so we're trying to actually get these second-order correlation measurements using a resonant excitation, and we expect that when you do that, the things should improve significantly. But this result is a little bit of cheating. Because even though we get the 2 dots and 2 cavities on resonance on the chip, we're observing the 2-photon interference off chip. We actually just pull both photons off chip and use bulk optics to collide them on a beam splitter. We would really want to be able to do this on chip so we can start to interact them with chip integrated waveguides. And so to do that, we decided to go for a simpler device, not use cavities, but simply use 2 waveguides. And the idea here is we took a single photonic crystal waveguide and segmented it into 2 pieces, thermally isolating them with this slit here that's connected by this tiny bridge so that we can heat this segment of the waveguide independently of this segment. And then we simply need to find 1 dot in this segment and another dot in this segment that are within the tuning range of each other. And then we can use the thermal tuners to kind of bring them onto resonance, and then we can look at their coupled emission into the waveguide. And what happens when you do that is that if you excite both dots, when they emit a photon, they actually don't emit it independently. They emit a photon into a bright state, which is a bright superradiant state, which is an entangled state of one emitter being excited and the other one being in ground, and the other being excited and the first one being in the ground. So it's actually an entangled state, and because of that entanglement, you end up with a doubling of the spontaneous emission rate to the ground state. So what this means is that when you look at the second order correlation measurement, you get a doubling of the G2 at 0 time delay due to this doubling of the rate and into the ground state. And when you look at this, you might say, well, that looks exactly like the 2-photon interference effect that I observed, that you showed me in the previous slide when we had 2 dots independently colliding on a beam splitter. And it is exactly the same thing because there's actually a one-to-one analogy between superradiance and 2-photon interference, which you can prove, but maybe it's not so important for this talk. The bottom line for this, the only point I'm trying to make here is that we can observe this superradiant effect by looking at the G2. So if we have the 2 dots at the same wavelength, we see this this enhanced G2. And then if we tune one of them off resonance, we just see a drop to about 75%. It should be 50%, but these are not perfect single photon emitters, so we don't get all the way down to the ideal G2 of 0.5. Okay, so that basically tells us that we are starting to be able to couple multiple emitters both to cavities and also on a chip through waveguides. But still, to get one of these waveguide devices working, my student had to hunt through about 200 devices. So it's still not a high yield process. And so the question is, how do we make this, more practical? I mean, we can start to make more segments and try to get more dots, but the yield is going to continue to go down. And for that, so I think we've been exploring different fabrication methods that may get around a lot of these problems. And the point here is that when we make these devices, we have a 5% yield, which means if we make 1,000 devices, we have 50 working devices. That's a lot of devices. The problem isn't that we lack devices that work. The problem is that they're all in the wrong places. They're randomly spread on the chip. We have an array of say 30 by 30 devices, and somewhere in there, there's some working ones. But if you wanted to get 5 devices coupled by waveguides, you have to have at each point in the waveguide an exactly working device. So one way to do that is to simply make a large template of devices, find the working ones, then pull them off chip to a second chip that has the waveguides and the optical structures to it, so that you can get so that you can get all the working devices in the right place. And so we've been working on this pick and place technique for doing that. We have a focused ion beam system. So this is a large template of many devices, and then we use a focused ion beam to release one of them and pick them up with a microprobe. We then move that chip, which has the templates, and then we bring it onto another chip. This one has a lithium niobate waveguide on it where we've etched the window, and then by by pushing it around a bit, we can actually get a single device coupled to that waveguide. And in fact, so this is kind of one of the approaches we're pursuing is find the devices that work, pick them, and place them onto a second chip that has the optical waveguides. And the nice thing about that is it also alleviates a lot of the problems, the limitations of gallium arsenide. Gallium arsenide or indium phosphide are very good optical semiconductors, but they may not be the best material for making waveguides and circuits. In this way, we can actually we can just use the gallium arsenide for what it's good at, which is cavities and optical emitters, and then move them on to silicon nitride or some other material that's that's better for making very complicated optical circuits. And as a matter of fact, one of the things we recently did was just that. Since we are working with dots that emit at 1.3 microns, we are compatible with silicon photonics. So we use this pick-and-place technique to move multiple indium phosphide beams containing quantum dots onto silicon waveguides. And you can see here we have a series of silicon waveguides. And these four, we've placed an indium phosphide beam on each one of them. And this is 4 for 4. So this is basically this means the success rate was, well, I don't want to say the success rate is 100% when we only have 4 data points, but what I'm trying to say is that the success probability is relatively high. We didn't have to find one here and then screw up 5 waveguides and then the 6th one works. We're actually able to get devices in the right place, and they're actually coupled. We can see emission from the silicon waveguides due to the quantum dots, and in fact, using these Y splitters, which act as an on-chip 50-50 beam splitter, we can actually do a correlation between the two grading couplers, and we see anti-bunching due to a single dot in the beam. So we're starting to be able to couple these photons to silicon waveguides. And there's other materials we can, of course, explore, silicon nitride, and I think there's aluminum or indium nitride. There's a lot of different materials that are suitable for working with these devices. So the hope is that by pre-characterizing just the working devices and then using this type of pick-and-place technique, and this is not the only way to do it. There's other people working on other ways to pick things up and place them using fibers and PDMS stamps. But using these kind of deterministic fabrication techniques, we can start to fabricate devices composed of multiple dots, multiple cavities that are actually working collectively at the right wavelengths. Okay, a few other side projects or related projects that we've been working on. One is, once you do this, what useful things can you do with a device composed of single photon sources and linear optics? And one of the things we've been thinking about is other protocols, other things you can do for secure communication. There's certainly been a lot of work on using single photons as for cryptography and for preventing eavesdroppers from determining what messages two people are sending across a network. But the message security is only one type of threat. There are other ways that an eavesdropper can extract information from the network. For example, knowing who is communicating to whom is also another important form of information. For example, if you go to the internet and you go on a website and you look up heart conditions, if your insurance company is monitoring the fact that you're communicating to a website that gives you information about heart conditions, they might start to infer, well, maybe something's not so good with your heart. Maybe you're not going to be doing so well. Maybe it's time to cancel your insurance because you're not as low risk of a patient as they initially presumed. So just the fact that somebody's talking to somebody else, just knowing the identity, can actually yield a lot of very important information. This is at the heart of something that in network security they call traffic analysis. And so we've been looking at whether quantum signals can protect a network from traffic analysis. They can prevent an eavesdropper from analyzing the traffic flow through a network. And we devised a protocol for doing that, which relies on superpositions of packets going through the network. So by creating a superposition of whether a packet is sent from Alice to node B or node C, the network can actually identify when there's an eavesdropper, because if the eavesdropper tries to figure out whether the packet is going to node B or C, she destroys the superposition by inferring which path information. And by making a measurement, the network can actually determine whether an eavesdropper is trying to infer this information, and it's very similar, analogous to BB84. You start to get rowdy, you start to get errors, and those errors reveal the presence of the eavesdroppers. The nice thing about this protocol is it only requires single photon sources, routers, and detectors. So it's doable with technology that we conceivably have today. And so it's not something that we have to have these large macroscopic entangled states of many memories over kilometer distances. It requires just single photon transmission. So if you want to know a little bit more about this, we have a description on the archive where you can get more details. We've also been looking at some more fundamental studies of the interaction of these photonic crystals with topological photonic structures. So there's another field of research that people have been working on, and particularly one of my colleagues, Mohammed Hafezi, which is how to translate effects in condensed matter physics into the photonics regime. So one of the things that he's been very interested in doing is using photonic structures to realize similar effects to topological insulators in condensed matter. And so one of the ways to do that is to take a photonic crystal which has a honeycomb or hexagonal periodicity, and you perturb the unit cells by either shrinking and expanding them. And what's very interesting is that when you do that, you open up a band gap. But if you do one type of perturbation, you open up a topologically trivial band gap. So if you shrink them, you open up a band gap that's topologically trivial. You've basically converted the symmetry from hexagonal to triangular. So you open up the band gap, but it's a trivial band gap. Well, if you expand them, you actually open up a topologically non-trivial band gap that has a inversion of the p and d orbitals of the band. And so once you sandwich two of these perturbed materials together, you actually get a edge state because it's analogous to an interface between two topological insulators with different topological invariants. And because of that, you can directionally route light around sharp bends. And so there's a lot of analogy between these kind of structures and the condensed matter structures. And so we've been working to realize these kind of effects in using photonic crystals. And we've been using dots as effectively a local probe for measuring the chiral behavior of these waveguides. So if you put a quantum dot in one of these waveguides and you apply a magnetic field such that it emits either right or left circular polarized light with different colors because of its Zeeman shift, we can then identify whether that we can then see that one circular polarization ends up in one end of the waveguide while another one ends up in the other waveguide. And this effect is robust even in the presence of a 60-degree bend. And so it exhibits a lot of the properties that the electronic topological insulators produce, which is unidirectional emission and as well as robustness. So this is still kind of a basic. This is still kind of a very in its early works, these ideas. But we're hoping that in the future we can use a lot of the strong nonlinearities that we have in these cavities. We can somehow incorporate them into these topological photonic structures. And then if you can create strong photon-photon nonlinearities in these systems, you can start to see really interesting physics. There's been some theory work on realizing fractional quantum Hall states and other interesting many-body states in the system. This is a little bit beyond my understanding of physics. So if you want to learn more about this, we have a paper on it, and it'll describe in more details what we did in this experiment. So in conclusion, I hope that I've convinced you that that by coupling quantum dots to nanophotonics, we can actually start to create really strong interactions at the single photon level. And maybe we have some real reason to be optimistic that we might be able to scale this up to bigger systems. Some interesting future ideas to work with. Everything that I've shown you so far was done by reflecting off the surface of the cavity. But we've a while ago shown that you can observe very similar physics through a waveguide integrated structure, which is more conducible to planar interconnection. So moving towards that kind of a device platform would be very beneficial. There's been work on incorporating on-chip detectors that would certainly help us. If we can generate and detect photons on chip, our efficiencies should go significantly up. And if you want to do quantum information processing with photons, you need 99% efficiencies. So at some point, you're going to have to start thinking about keeping everything on chip. And so we have been talking to some groups, Carl Bergen's group at MIT, about whether we can start to incorporate these detectors onto chip. It's not trivial because there's a lot of background light issues, but it's been done, and we think it's a very interesting direction to go. And of course, now that we're operating at longer wavelengths, the entire domain of silicon photonics is available to us. So we could start to think about incorporating our emitters into more complicated photonic circuits and maybe realizing some sort of interesting interactions on a chip. So with that, I thank you for your attention. And I want to thank the people who did this work, my group, in particular, Shuo Sun, somewhere here. Oh, there you are, right in the center, who did a lot of the spin photon transistor work. Jae-Hyun Kim, who did a lot of the work I showed you on indium arsenide, indium phosphide dots, along with Shahryar Agahai, and also Sabyasachi Barik, who did the topological photonic work. And with that, I thank you and open up the floor for questions.
It's been a little bit long, but I think we have time for a couple quick questions, and then people can also come down to ask questions after the talk. So we're there. Xiaodong.
Question. You talk about a single photon switch, for example. What's the evidence actually is a single photon impact?
What we do is we look at a correlation measurement. So we look at, because we have low efficiency, what we have to do is we have to ask if there was a photon at the gate, what does the photon at the transmission do? And so it's a two-photon correlation measurement. When the photon in the gate is present, we see one effect. And that's done by a two-photon interference measurement. So that gives you basically a complete mapping of what happened when there was a photon at the gate versus not. And that's pretty strong evidence that this is a single photon interaction.
Okay, other questions? Arka.
You said like you have two gratings, silicon photonics, collecting light and doing the correlation. Do you have like a pinhole to select light from both the gratings, or?
Yeah, well, actually, we use like a pick-off mirror and kind of pick off one of them and couple them to different fibers. So once you magnify it, they're separated by something you can see on a card. So then you can pick them off. Nothing terribly complicated.
Thanks for the great talk. I was curious, when you shift the energy of the quantum dots photothermally, is the method shifting because of epitaxial strain with the substrate, or is it just a marginally bandage?
Oh, so that's a good question. So you're asking me why the band gap shifts in gallium arsenide. I might not be able to give you a very. I know there's lots of people who know the answer to that question. I might not be the one. In other words, why does the band gap get narrower with thermal shift? I don't have a good answer. Do you have one? I don't know. I'm sorry. I'll have to get back to you on that one.
Okay, with that, let's thank Ido.